magnetic field due to a current-carrying circular coil. We have already studied that when current is passed through a straight conductor, a magnetic field is produced around the conductor. This region of magnetic field can be represented as concentric circles around the wire. So we can say that a cylindrical shell of magnetic lines of force surrounds the entire conductor. The direction of these lines of force can be found by the right-hand thumb rule or Maxwell's corkscrew rule. Both these rules can be verified with a compass needle also. Now, modify the straight conductor to form a circular loop and pass it through the two holes in a cardboard. Connect the ends of the coil to an ammeter, a battery, a key, and a rheostat in series. Sprinkle some iron filings randomly on the cardboard. Switch on the key of the circuit and adjust the rheostat to allow a current of about 2 amperes to pass through the conductor. It can be seen that the directions of the current flowing through each arm of the circular loop are mutually opposite. Now, as we gently tap the cardboard, we can see that the iron filings align themselves in a specific pattern. They are in the form of circles around each arm of the conductor. These circles prove the presence of a magnetic field. To find the direction of these magnetic lines of force, we apply the right-hand thumb rule. According to this rule, we can find that the direction of the magnetic lines of force around the arm of the conductor with upward flow of current is anti-clockwise, while that around the arm of the conductor with downward flow of current is clockwise. In other words, as the direction of the current in each arm of the conductor is mutually opposite, the direction of the magnetic lines of force is also opposite to each other. Conversely, within the space enclosed by the coil, the lines of force are in the same direction. Let us study the various properties of the magnetic field produced due to the current-carrying circular coil. Observe that the lines of force are circular near the arms of the conductor. But as we move from the arms towards the center of the coil, the lines of force become almost parallel to each other. Thus, near the center of the coil, the magnetic field may be considered to be uniform. Hence, it can be said that as the distance from the center of the conductor increases, the magnetic field intensity decreases. At the center of the coil, the magnetic field is maximum and is directed perpendicular to the plane of the loop carrying current along its axis. Next, increase the current flowing through the conductor from 2 to about 6 amperes and tap the board gently. We can see that more iron filings get aligned with the magnetic field lines. That is, the number of magnetic lines of force increases as the magnetic intensity increases. Now, increase the radius of the coil. You can see that the magnetic field intensity decreases. The magnetic field produced around the coil proves that the coil behaves like a magnet and has a north and south polarity. The clock rule is used to find the polarity of a current-carrying coil. If we look at this particular face of the coil, we can see that the current is flowing in an anti-clockwise direction. Moreover, the magnetic lines of force emerge out of this face of the coil. Hence, this end is said to be the North Pole. Similarly, looking from the other side of the coil, the current is found to be flowing in the clockwise direction. The magnetic lines of force enter into this face of the coil. Therefore, this face is considered to be the South Pole. Hence, the clock rule states that when looking at one particular face of the coil, if a current is found to be flowing in an anti-clockwise direction, that face of the coil is considered to be the North Pole. If the current flows in the clockwise direction, that face of the coil is considered to be the south pole. Summary. A magnetic field is produced around a circular coil carrying current. The direction of these magnetic lines of force can be found using the right-hand thumb rule. The magnetic field lines are circular near the two arms of the loop but are almost parallel near the center of the loop carrying current. The magnetic field intensity decreases as the distance from the center increases. The magnetic field intensity can be increased by increasing the current flowing through the coil. On increasing the radius of the coil, the magnetic field intensity decreases. Lastly, using the clock rule, we can find the polarity of the current-carrying circular coil.